Hello, everybody. I am Drawn, and I'm going to be covering the basics of rotational kinematics in this video. So, this is what we're going to be covering next in AP Physics C, but this also works at AP Physics 1. Just whenever I say something like derivative or integral, if you're in Physics 1, you can ignore it. If you're in Physics C, then don't ignore it. So, the most basic thing that we're going to start off with is the fact that we are no longer going to be using degrees, we are going to be using radians. And the reason we're going to be using radians is because they give us this fundamental relationship in which the radius times phi or phi, which is going to be in radians, equals to the arc length, which is often notated as s. So this relationship is very important. I'm sure you've learned it already in your math classes, but this makes things a lot easier for us. And if you're in calculus, you only use radians really, you don't really use degrees. So usually we're going to be using radians when dealing with angles because we are dealing with angular rotations after all. So for the exact conversions, 1 radian is equal to around 57.3 degrees. Pi radians is equal to 180 degrees. So if you imagine a circle, pi radians is right over here. This is 0, and this is pi over 2, 3 pi over 2. If you know unit circle, you know this. And this is essentially like 180 degrees from here to here. So that's a very fundamental relationship to know because it also tells us how many revolutions are in 1 radian because we have 2 pi radians is equal to 1 revolution. So 1 radian it has about 0.159 revolutions. So what exactly is angular movement though? What is angular kinematics? Well, essentially say we have this point P. Essentially I should probably erase some of this term before. Um, it's essentially if this point P was moving through this rotational sort of thing. It's not orbiting around it. It's like the whole thing is moving, but we're essentially choosing point P to be our reference frame to trace like how much movement has happened. So don't confuse it with orbiting motion because orbiting and rotational motion are different. This is more akin to like a spinning top, or if you were to take your pencil and spin it around in your hands, or any sort of rotating thing, like a wheel basically rotating. It's not an orbiting. So don't confuse this for orbiting things. But that is going to come in later. So the most important variables are going to be velocity, acceleration, and displacement for kinematics, of course. So we basically measure displacement in radians displaced, usually. So it's going to be phi or delta phi is going to be our displacement. So we know that from regular kinematics that change in displacement over change in time is equal to velocity or average velocity. Or if we are in calculus, you know that d change in displacement equals to over dt is equal to instantaneous velocity. So we have the same sort of relationship here, where angular velocity is notated with this like sort of w omega shape, lowercase omega, and it's equal to delta radians over delta t or d radians dt. I'm just gonna say radians because I think phi is kind of hard to like absurd weird to say. So. And then we also have that angular acceleration is equal to change in velocity, angular velocity over change in time. Normally it's gonna look different. Like I know the W's look kind of like work, um, but normally in actual problems they'll be notated very easily, so you can easily tell the difference between like a rotational kinematics question and a work question. I mean they might be interjoined, but usually the like when you're dealing with angular velocities, it'll be pretty obvious, like the W shape, because it looks quite different. If you search up a lowercase omega, I think it is. So angular acceleration is equal to change in angular velocity over change in time, or d angular velocity over dt, or the derivative of respect to time. And our integral relationships, so if you're in physics C, our integral relationships still work here. So integrating acceleration with respect to time will give you angular velocity, and integrating this with respect to time will give you angular displacement with the constant at the end. But these relationships that we know from kinematics still hold here. The next thing to cover is going to be our equations. And these equations are pretty basic. They're the same ones actually as the ones in regular kinematics. All we did was substitute them out for our angular variables. So here are the equations. You know them, you love them. Definitely memorize these because I think these are annoying to like go back to the formula sheet and look at over and over again. And they're pretty easy to memorize, I think. So and then we also have this one special one right here, which you don't really see very often. But if you're ever given final velocity and time and acceleration, and you need to solve for like, you need to solve for any of these things, You can use this because it's essentially like a reverse of the original equation. Um, it's like this one's like kind of overshooting the area under the graph by multiplying final velocity times time, and then it accelerate like it counts that acceleration as something detracting from it, which is the opposite of what we had in the other one. And then we also have this fundamental relationship, which I covered earlier. Um, so the next thing we need to cover is sort of the connection between like the linear velocities, linear accelerations, and angular velocities, angular accelerations. And this is going to be in the form of tangential velocities and tangential accelerations. Because obviously, if you have like a ball rolling around, right, it's going to have like it's going to rotate, yes, but it's also going to have this velocity down here that's like how far it's going, or that sort of thing. So basically, this is based off the relationship that we know that ds dt, which is basically velocity because ds is like, actual length. It's how like arc length. That's how much is moving. So it's the velocity. And since radius is always kept constant here, like this, what's actually going to be changing is going to be d phi dt or d phi dt. It's going to be the main thing. And we know that d phi dt is equal to angular velocity. So we know that velocity is equal to angular velocity times radians. And this makes sense, right? Because if you think about it, we had the change in like the radians times radius was equal to this like s arc length. So basically, we're just putting it in terms of velocity now. For tangential acceleration, it's based off the a similar relationship where basically a change in velocity over change in time is equal to dw dt times radius. And we know that dw dt is equal to radial acceleration. So we're going to multiply that times radius to get our tangential acceleration. So these relationships are very important to know if you're ever solving for one of them. Like if you're given a very basic problem where you have any two of these and you're solving for the other one, it's pretty simple to do so. There's also radial acceleration, so it's kind of like how we had centripetal acceleration, but this is going to be in terms of angular units, basically, um, angular dimensions. So we know that or centripetal accelerations, I should say, is v squared over r, and we know that v is equal to w times r, so we do w squared times r squared over r equals to w squared times r, because you can see the math down here. So this is essentially our centripetal acceleration. So that's essentially it for rotational kinematics. The kinematics section is usually pretty easy. It becomes a bit complicated when you have sorts of like, while the thing is moving, it also has like angular kinematics and then translational kinematics to deal with. That's when things get a bit more complicated. And then torque on top of that also makes things more complex. But for kinematics, really, the basics are very much the same as regular kinematics. Just we're going to be dealing with changes in angles instead of changes in like, length or however far we move. So that's essentially it. Thank you for watching. I will have a video on torque tomorrow. I'll try to have the entire unit uploaded before school starts again. I hope you guys like, subscribe. Thanks to Physics Club officers and me for doing this. Yep. Bye.